Oi, 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 oi.
Hello everybody, welcome back to Planet X News. It is October 7th, 2017. And ladies and gentlemen, we have made another Planet X discovery, once again, near the sun. Now, I have the current SDO 48-hour loop up on the screen right now. And listen, ladies and gentlemen, a lot of solar scientists and scientists from NASA, they are claiming that our sun has entered into what they refer to as the grand solar minimum.
Solar minimum is coming. Presented by Science at NASA. High up in the clear, blue noontime sky, the sun appears to be much the same day in, day out, year after year. But astronomers have long known that this is not true. The sun does change. Properly filtered telescopes reveal a fiery disk, often speckled with dark sunspots. Sunspots are strongly magnetized and they crackle with solar flares, magnetic explosions that illuminate Earth with flashes of X-rays and extreme ultraviolet radiation. The sun is a seething mass of activity. Until it's not. Every 11 years or so, sunspots fade away, bringing a period of relative calm. This is called solar minimum, says Dean Pesnell of NASA's Goddard Space Flight Center in Greenbelt, Maryland, and it's a regular part of the sunspot cycle. The sun is heading towards solar minimum now. Sunspot counts were relatively high in 2014, and now they're sliding toward a low point expected in 2019 to 2020. While intense activity such as sunspots and solar flares subside during solar minimum, that doesn't mean the sun becomes dull. Solar activity simply changes form. For instance, says Pesnell, during solar minimum we can see the development of long-lived coronal holes. Coronal holes are vast regions in the sun's atmosphere where the sun's magnetic field opens up and allows streams of solar particles to escape the sun as the fast solar wind. Pesnell says, we see these holes throughout the solar cycle, but during solar minimum they can last for a long time, 6 months or more. Streams of solar wind flowing from coronal holes can cause space weather effects near Earth when they hit Earth's magnetic field. These effects can include temporary disturbances of the Earth's magnetosphere, called geomagnetic storms, auroras, and disruptions to communications and navigation systems. During solar minimum, the effects of Earth's upper atmosphere on satellites in low Earth orbit changes too. Normally, Earth's upper atmosphere is heated and puffed up by the ultraviolet radiation from the sun. Satellites in low Earth orbit experience friction as they skim through the outskirts of our atmosphere. This friction creates drag, causing satellites to lose speed over time and eventually fall back to Earth. Drag is a good thing for space junk, natural and man-made particles floating in orbit around Earth. Drag helps keep low Earth orbit clear of debris. But during solar minimum, this natural heating mechanism subsides. Earth's upper atmosphere cools and to some degree can collapse. Without a normal amount of drag, space junk tends to hang around. There are unique space weather effects that get stronger during solar minimum. For example, the number of galactic cosmic rays that reach Earth's upper atmosphere increases during solar minimum. Galactic cosmic rays are high-energy particles accelerated toward the solar system by distant supernova explosions and other violent events in the galaxy. Pesnell says that during solar minimum, the sun's magnetic field weakens and provides less shielding from these cosmic rays. This can pose an increased threat to astronauts traveling through space. Solar minimum brings about many changes to our sun, but less solar activity doesn't make the sun and our space environment any less interesting. For more news about the changes ahead, stay tuned to science.nasa.gov.
Over the course of the last couple of months, Dr. Elbers and I, we have been trying to put together this cycle. And the cycle that I'm referring to is the rotational path or the orbital path of this object that we're referring to as Planet X, because I've discovered it yet again, and we'll get to those photographs at the end of this video. I also discovered, once again, this object near the sun. And I mean very, very close, ladies and gentlemen. I mean, it is very close. It is so close that it actually gets enveloped in the sun's corona. And once again, that is exactly where I found it this morning. Now, getting into this photograph. I snapped this photograph on October 4th. As you can see right down here in the lower left-hand corner. This is a composite image of 3 different angstroms, the 211, 193, and the 171. Now, in the few minutes that you were sitting here listening to me talking about the sun, I'm just wondering if you were able to pick out and find the object in this photograph. If you haven't, well, let's just zoom in and I'll show you. Here it is, right here. Right there. Sometimes it is hard to see because it gets enveloped. And there's the object, right there. And it's pretty massive. Our calculations is this object is definitely much, much larger than the planet Jupiter. Much larger. In order for it to get this close to the sun, it has to be a star, not a planet. So this is the original photograph that I was looking at. And, you know, my eyes are so trained now that I can spot these objects very, very quickly. But there it is, folks. I mean, you can clearly see it right there. Now, that's not a plasma loop. It's not a prominence. That is a perfect spherical object right there in the corner. Now, this was the actual original that I had picked up. Now, I wasn't able to pick this up from the SDO. I actually had to go over to the SETI website, and because I noticed that there was time missing on the SDO footage. When I see time missing, I know something is awry. So I immediately went and started looking for the missing footage. When I found the 6 hours of missing footage, bingo, that's what I find. Right there. They're painting a pretty bad picture for themselves because they're not doing that good of a job hiding it. Now, in this photograph, if you just take a look at this burnt orange color right here. Now, this is the sun's corona, and this is in the 304 angstrom. So the sun's corona is not going to show as this huge, bright, illuminated glow. It's going to be very, very close to the sun. You can see the object is slightly blocked, but you can see it right here. Same photograph, different angstrom of light, but there she be. Move to the next photograph. Again, same photograph, different filter, and again, this is a composite between the 211, 193, and the 171. And these are just different angstroms of light. And we could see it right there. And you can clearly see, you could almost see some markings on it, but again, you know, that could be slightly distorted by the light and the activity on the sun, and also the corona being directly in front of this object. So that's why it's always going to look hazy. We're probably never going to get a really, really clear view of it because of the sun's corona. If this object were to get any closer than it is now, we're in serious trouble. Big time. Now, that's not a plasma loop. It's not a prominence. That's not a plasma loop. It's not a prominence. my eyes are so trained now that I can spot these objects very, very quickly.